Hey, good evening, Dr. McBride.
Good evening, Madry.
How you making out? How was your Thanksgiving?
It was fine. Yourself?
It was all right. I'm glad that I had the time off because I really needed that time to try to do that, do these last two assignments.
Yeah,
So,
I hear you. I always
uh,
think that this class is poorly timed.
yeah, well, that break couldn't have come at a better time. Couldn't have come at a
I'm
yeah,
glad it worked out for you.
I got to the mini project and I got my score back and I was like, dang, I felt like I was doing better. I started off, kind of rough, and then my grades increased, and then I got to the mini project. I'm like, damn, I get slapped back down again. So this is one of the classes that's been pretty challenging to me. Statistics has always been challenging.
Yeah, it's a tough one for sure.
Yeah, it's been challenging. So well, hopefully I can rebound on this week 4 assignment and this and our post for the week.
Oh yeah, I'm sure you'll be doing fine on the post. The truth of the matter is, the only time people don't get full credit on the post is if they just don't do the work or they plagiarize. I mean, really, it's one of those things.
Yeah, on the post on this week's post, I tell you, it's hard as the dickens to find an article that has good data to describe.
Yes, yes.
It
And I apologize, I should be more specific. You don't have to worry about the article actually having the data, just as long as they have some sort of statistical analyses in it.
Oh, okay. That, because I was looking for, tables and graphs and charts.
Which are great, but you don't have to have them that, like list the specific data. If they just give you some results, that's all you need to talk about.
Okay.
Yeah.
Because in dealing with what I'm trying to deal with, just I'm dealing with school turnaround,
Right.
public school turnaround, and there's a lot of statistical data to analyze. And so if I don't have to look at a data table or chart or any kind of plotting, I can actually go through and talk my way through what's going on with the data from the different articles that I've looked at.
Perfect. Yeah, because that's all you need to do is find an article that just discusses the data, right? Discusses some results, and then you're discussing that. You're giving a summary of what the article's about. Give a summary of what the results they present, and then just discuss any good or bad things about it. Just look at the instructions and kind of use them as a guide, but don't worry about finding an article that has the actual raw data. You just have to find an article that has some sort of statistics in it.
Okay, I missed probably a big chunk of what you said. You said give a discussion regarding the data, and
yeah, just find an article that has some sort of statistics in it. You don't have to worry about whether or not it has the raw data. And then all you got to do is just kind of discuss the article, right? Describe it, give a summary of what the article's about, what the findings were, the statistics that they presented. Were they good stats, bad stats, as far as did it look like they kind of did everything right, or did they leave some stuff out, or maybe there were some results that you wish they would have included that they didn't, those kinds of things.
Okay, which makes sense.
Yeah.
Okay. All right, that makes sense.
So hopefully that'll make it easier on you finding an article.
Yeah, most definitely.
Good.
All right, I'm going to talk to my vice principal.
All right. Well, even though there's only 3 of us, let's go ahead and get started. So this week we're going to learn all about probability. And let me just start off by telling you that you do not need to be an expert in probability to understand statistics. Probability is always taught as part of a statistics course because you just need a basic understanding of the basic concept of what probability is and how, at its most basic sense, probability is computed. And really that's it. Anything beyond that, you would only need if you were going to be, an advanced statistician like myself or somebody like that, right? Otherwise, You don't need to know anything other than just the basic probability stuff. And so that's why I'm going to keep harping on you guys to watch my videos, because I break it down to the basic concepts. I don't teach all of these formulas. You don't need to memorize all these formulas. You don't need to use all these formulas, because you're not going to be, actuaries and people who actually do probability for a living. So there's no point in you wasting your time learning all those formulas. Just understand the basic concept of what probability is. And it really boils down to this very simple concept. Probability is good over total. That's it. It's the number of good ways you can do something divided by the total number of ways you can do something. So for instance, you roll a 6-sided die. You ask the question, what's the probability that it comes up an odd number? All right, well, how many good ways can that happen? Well, how many odd numbers are there on the die? 3 of them, 1, 3, and 5. Okay, so there's 3 good ways out of how many total ways? Well, there's 6 total sides of the die. So it's 3 over 6, it's 1/2, it's 50%. It is literally just that simple. That is probability. Now, granted, probability questions can get very complex and they can involve very complex formulas to figure them out. But all of the questions that you're going to be faced in the homework and stuff like that are all going to be basic enough that you can do them with the simple good over total technique. That's all we're doing. That's all we care about. Okay, so before we move on to that, just some quick notes. I have graded everything from week 3, including the mini projects. So please check it and make sure you're all good to go with that. Again, this week, you have to have your article critique posted by Thursday, but then your minimum of 2, you can do more if you want, but your 2 minimum replies aren't due until Sunday. There may have been some misunderstanding as to what you need to be finding as far as these articles are concerned. You do not need to find an article that actually has raw data in it or, list the data or anything like that. You just need an article that has some sort of statistical analyses in it. Does it talk about the average of something, the median of something, right? Standard deviation, whatever. Basic statistical analyses, any kind of analyses, even if they're advanced statistical analyses, that's great too. But just as long as it has some stats in it, that's all that matters. And then you just basically follow the instructions of what it tells you to do. You give a summary of it, of the article itself. You talk about the findings, you talk about the stats, you talk about, what was good, what was bad, what you wish they would have done, those types of things, and you're good to go. So that's that. You may notice that in the grade book in Canvas, the article critique is only worth 65 points when it's supposed to be worth 100. And that's because, like I said, a lot of these things I try and adjust, but I can't adjust them because they're cemented in place by the university. So you might notice that there is a second assignment that says like critique replies that's worth the other 35 points. And the nice thing about it is I made the 65-point one due on Thursday, because that's when your critique is due. And then the 35-point, your replies, is due on Sunday. So that'll help remind you that you need to post, right, your critique by midnight Thursday to get those 65 points. And then the last 35 points come from your 2 replies, and those aren't due until Sunday. Okay. Questions at all on any of that stuff? All right. So let's look at some probabilities. So here's a nice little table of data, right? This would be what we consider, this would be a cross tabulation, right? Where we've got data that is categorized 2 different ways, by color and by whether they say yes or no. So you can imagine that these were maybe ping pong balls that were colored yellow, red, and blue. And on those balls were either written the words yes, no, or maybe. Or maybe they were slips of paper, yellow, red, and blue slips of paper with the words yes, no, or maybe written on them. And they were all thrown into a bag or a hat or a basket or whatever. There were 227. We're going to go with slips of paper just because I don't want to keep saying balls over and over again. And then this table, this is a cross tabulation, right? It gives you the frequencies of those slips of paper with your 2 different variables, this being words and this being colors, right? So we can see that there were 30 red slips of paper that said maybe, and so on and so forth. So if you reach into the bag and grab a slip of paper at random, what's the probability that it's yellow? Well, it is simply just good over total. There are 90 yellow slips of paper over 227 total slips of paper. So what would be the two numbers? What would be the good over total if we were going to do yes? Anybody want to tell me?
So what was the question? Dr.
So if
Miller?
we did the second one, what's the probability that it was yes? It'd be what over what?
It will be
It
all
will
the
be-
yes answers. It will be 92 over 227.
Perfect. Madri, how about giving me a no? What would no be?
No would be 40 over 227.
Perfect. All right. So obviously blue would be 55. Okay, now let's get a little trickier. How about we want to know the probability of yes and red? Anybody want to take a stab at that? What would you
32
think?
over 227.
Sorry, what was the number?
32.
32 over 227. Very good, because those are the ones that are red and yes, right? So maybe and blue, obviously 40 over 227. So awesome. Ands are pretty easy, right? Good job. Okay. What about ors? Now, when we do ors, they give you these formulas where it's the probability of A plus the probability of B minus the probability of A and B, blah, 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 blah. Oh my God, it's such a big pain in the butt. No, just think about it, right? If it has to be yes or red, then just add up all of the reds and all of the yeses and just don't add the 32 twice, right? So it's basically 50 plus 32 plus 10. Those are all the yeses. And then we add in the other 20 and the other 30 for the other two reds, right? A lot of people would go, well, it's just 82 plus 92. Well, no, it isn't, because when you do 92 plus 82, you've just added 32 twice. So if you wanted to do that, right? So if you wanted to kind of visualize, okay, so here's all the red, which is 82. Here's all the yeses, which is 92. Can we all see that 32 got circled twice? So that's why you would have to do 82 plus 92 minus 32, or you could just add, right, those five numbers. Either way, you get the total over 227. And if we do the maybe or blue, right, it's the same darn thing. So you can add up the two totals and subtract the crossover, right? Subtract the intersection, or you can always just add up the individual numbers, because it still comes back to this is my good over this is my total, right? All right, questions on those?
No question on those, but could you go back to the slide before this one? I just wanted to see something that I thought I missed.
Go for it.
Okay, let's see. It makes sense. Okay, it's making sense to me. I was looking at something and it didn't make sense at first, and so now it does.
Okay.
Because I guess I just didn't look at one of the numbers.
Yeah, that's easy to do. Okay. Now, here is given condition, right? So whenever you see this little vertical line, that means given. So this is the probability that A happens given that B has already happened. Okay, so this little vertical line is always the word given. Now, given conditional is called conditional probability. And when you have conditional probability, there is a very fancy formula for figuring these things out. But again, I'm not a fan of formulas, because you guys don't need to learn formulas, because you're not doing this for a living, damn it. It still comes back to good over total. So the only thing that changes when you have a given condition is your total changes, because instead of looking at all 227 things, I'm now telling you something specific about the thing that you chose. So this says you pick a slip of paper and you already know that it says yes, because you're given that it says yes. So you've grabbed a piece of paper and it says yes. And now the question is, well, given that we know the piece of paper says yes on it, what's the probability that it's yellow? Well, if we're told that it says yes on it, then we know the total is now 92. So this has to be 92 for my total. So now out of those 92, how many of them are yellow? Well, 50. So it's 50 out of 92. Does that make sense? Let's try another one. How about no and blue? Can somebody give me what our new total will be when we're trying to figure out the probability of no, given that it's blue. What's our total going to be?
Is it 55?
Very good, Vandana. It's exactly 55, because if we're told that it's blue, we're only looking at the blue stuff. So now amongst those 55 blue things, how many of them said no?
5. So
Very
5
good.
of-
Yep, 5 over 55. It's that simple. All right, let's try yes out of yellow. What's our new total going to be if we're given that it's yellow?
90.
Awesome. And out of those 90 yellows, how many say yes?
50.
Yeah, look at that. 50 out of 90. Nice. All right, last one. If we're given that it's red, what's our new total?
82.
82. And out of those 82, how many say maybe?
30.
There you go. It's that simple, guys. Don't overthink it. That's conditional probability. It's literally just when they give you that condition, it resets your total. And instead of looking at everything, you're only now looking at that little subset of things. And the stuff doesn't have to be in a table. It's very nice when it's in a table because it's very easy to visualize what's going on. But even if they just describe the situation, you can still calculate the good and the total from the situation. They're always going to give you enough information that you can just do it that way without having to use the silly little formulas. Okay, the next thing to know is that when you see a little horizontal line on top of something, that means complement. And the complement of something just means every other possible outcome besides that thing. So the probability of red with a line over is basically saying the probability of it not being red. And if it's not red, it has to be either yellow or blue, right? So it's literally going to be just 145 over 227. It's that simple. Same thing here. If we can put it together and have a given with a not, right? So remember, this is given. So now instead of looking at the entire total, we're only going to be looking at those things that are not yes. So if we're not looking at yes, that means we're looking at these things, which means this is our total, right? So now we know our total is going to be 135. It's going to be something over 135. And the something is the blue, right? That's the good stuff. So out of this, how much blue do we have? Well, here's blue, here's blue, right? So shouldn't it just be 45 out of 135? Bam. And that's conditional probability lumped together with a complement. A complement simply just means everything else. Don't think of it as the opposite. It's not always the opposite because, for instance, the opposite of yes would be no, but the complement of yes is no and maybe, right? So the complement is every other possible outcome, every other way that the experiment can have a result other than your thing you're talking about, right? So, you know, flip or roll a 6-sided die, the complement of 3 would be 1, 2, 4, 5, and 6, right? All the other numbers except for 3. It's that kind of thing. Okay, questions so far on any of those? All right, well, again, please watch my videos on the basics of probability to learn good over total. And that's really all you'll need for the homework. There's a lot more videos in there that goes into a lot more detail than anything you'll ever need. Really, if you just understand good over total, that's pretty much all you need for the homework. Okay, discrete versus continuous variables. This is very important. We talked about discrete versus continuous in week 1. The big difference between discrete and continuous is discrete is counted, continuous is measured. Now, it just so happens that continuous variables can have decimals. They don't always have to have decimals, but they can. Discrete will always only be whole numbers because when you count something, you can't count a half of something, right? So discrete variables come from questions that ask you how many. How many TVs do you own? How many times a week do you eat out? How many children do you have, right? All of these are discrete variables because the answers, right, the numbers that would go into those variables would all be whole numbers. You would say we eat out 3 times a week, we own 4 TVs, we have exactly 2 children, right? It's those types of things. Whereas continuous variables are measured. How tall are you? How much do you weigh? How much money do you make? How long have you been a teacher, right? Because time is a unit of measure, right? It's things it's measured. So anything that's measured is going to be a continuous variable. And oftentimes the data that you gather are still going to be whole numbers, right? If you ask somebody how old they were, they wouldn't say 35 years, 12 months, 2 weeks, and 3 days, right? They would just say, I'm 35. Even though age is a measurement because it's a measure of time and it's a continuous variable, it's often reported discretely, right? Everybody's always going to report their age rounded to the nearest year. Same thing with height and weight, right? If you ask people for their weight, they're going to round to the nearest pound or kilometer. I'm sorry, kilometer, pound or kilogram, right? If you're anywhere else other than the United States, even though you measure someone's weight, and ergo it is a continuous variable, it would be reported by your subject in a discrete manner. So I point that out because continuous variables don't always have to have decimals. When you look at the raw data could all be integers, they could all be whole numbers, but it still represents a continuous variable. It just so happens that the data you got was reported rather than measured, right? If you actually brought in 100 random people and you weighed them all, you stuck them all on a scale and weighed them, then you would have decimal answers, right? Okay, this person is 125.6 pounds. This person is 203.7 pounds, right? You would have decimals because you'd be weighing them. You'd be actually measuring it, and depending on how accurate your scale is, maybe you could even get 2 or 3 decimal places of accuracy. Same thing with their height, right? If you were measuring people, you wouldn't just say they're 6 foot tall. You wouldn't even say they're 6'4". Maybe you'd say 6'4.5", right? You would get smaller and smaller increments because you would be measuring rather than just self-reporting. So that's a big difference of, how your data comes out to be what it is. But the bottom line is what's most important is discrete are things that are counted. Continuous variables are things that are measured. Okay. Once we've got that figured out, then we have 2 different types of probability distributions. We have discrete probability distributions, and then we have continuous probability distribution. So the discrete probability distribution is simply just a listing of all of the possible discrete outcomes that you can get from your experiment, and then the associated probabilities with them. So in this particular experiment, the answers could be 0, 1, 2, or 3. So maybe you ask people something like, how many children do you have? And it just so happens that nobody has more than 3 children. But in this population of people that you ask this question, 10% of the people don't have any children, 25% have 1 child, 45% have 2 children, and 20% have 3 children. So this is a probability distribution that represents that sample of data or population data, right? We can use it for either. But in any case, that's what a discrete probability distribution is. It's simply just the value of the outcome and its associated probability. Some things to realize. The probabilities always have to add to exactly 1, because if they don't, it's not a true probability distribution because it's missing something. And if it adds up to more than 1, then you're really screwed up, right? So just like, anything else, probabilities always have to add to 1, right? That each roll of the die has 1/6 probability, and there's 6 of them, so that adds up to 1, right? 50% chance that it's heads, 50% chance that it's tails. Half plus half gives you 1, right? So probability of flipping a coin, right, is always 1. It's always a 1 for the entire experiment. So it's the same thing here, that they always have to be a 1. If we want to know the probability that X is greater than 0, just realize that that would be 25 plus 45 plus 20, which equals 90. Or of course you could do 1 minus the 10%, because this is the complement of what you're looking for. Probability of at least 2. So this is where these things are going to get tricky. It's only going to be because of the English. You have to know that at least 2 means 2 and 3 are both correct answers, right? Those are both still good. So that'd be 65%. But the probability of no more than 2 means 2 or less. So that would be 0 plus 1 plus 2, and that would be 80%. So it's really going to be the English of these, phrasings that's going to be difficult. Everything else is pretty straightforward. Now, the binomial experiment and the binomial distribution is the most commonly used and most widely understood and known version of a discrete probability distribution. So it is important that you understand how the binomial experiment, how the binomial distribution works, what it represents, because it comes up a lot. So here are the general rules for an experiment to qualify as a binomial experiment. If your experiment can only have 2 outcomes on each attempt, i.e. you flip a coin, it either comes up heads or tails, right? There's only 2. You ask a bunch of people a survey question where they only have 2 choices, yes and no, or like and dislike, or whatever it is, but they only have 2 choices, right? So that would be each attempt, each kind of trial of the experiment has only 2 outcomes. It must be repeatable, which means you can do it over and over and over again. You can flip the coin over and over and over again. You can ask people that same survey question over and over and over again. And what's important is every time you repeat it, the probability of what we consider a success needs to remain the same on every single trial. Every time you flip a coin, if getting tails is considered a success, then that probability has to remain constant, and we all know it does. Same thing if you were asking people a survey question and getting an answer of yes was considered a success, then the probability of that happening would have to remain constant over every trial. And obviously it's 50% each time. But what would happen is once you got a large sample and you saw that 70% of your people said yes, then that would become the probability of your success. And then the idea is if you went and redid that experiment, you should see roughly 70% saying yes again, this kind of same probability thing. There is a variable, there are variable counts for successes, meaning if you ran this experiment a certain number of times, you could actually count up how many successes you had and then how many failures you have. So for instance, if you roll a die, there's a 1/6 chance of rolling a 5 on each attempt. So n is the number of times the die is rolled. X is the number of times a 5 comes up, because that's going to be considered our success. So now we've set up something that's a binomial. Even though a die has 6 outcomes, the numbers 1 through 6, if we set up 5 as being our success, everything else is considered the non-success or the failure. So even though there are 5 other ways that the die can come up, they're all lumped together as the second outcome. So that's the nice thing about a binomial experiment is even if you have an experiment that has more than 2 possible outcomes, like rolling a die has 6 possible outcomes, right? It can come up the numbers 1 through 6. Well, we can force it into being a binomial by simply defining 2 outcomes. There's the outcome of getting a 5, and then there's the outcome of not getting a 5. We could have done the outcome of getting a 5 or a 6, and then the outcome of not getting a 5 or a 6, right? You could always put it into basically 2 camps, the success camp and the failure camp. And then you just put however many outcomes do the success and how many outcomes don't do the success in each of the 2, and it still fits the definition of a binomial. So don't think, so again, if we go back to the survey question, they don't have to have only 2 options, yes and no. You could give them yes, no, and maybe, but it could still be a binomial if yes was a success and no and maybe put together was not the success. Or maybe no was the success and the yes and maybe were put together as the not success, right? So you can always have multiple outcomes as long as you split them into 2 options, and then that satisfies the rule of being a binomial.
So, Dr. McBride, if I was looking at this as a basketball player shooting free throws,
Right.
how would I describe this then?
Well, shooting free throws, they either make it or they don't make it, right?
Right, it's only 2 options.
Right. So that's a perfect binomial.
Okay.
And then
Right.
what you would do is you would figure out, okay, player X comes up and he's going to be at the free throw line. And in the past, from him throwing free throws as many times as he has, we know that he makes his free throws 35% of the time.
Makes sense now. Okay.
So that would be the probability of a success.
That's the probability of success, 35. Okay. That makes sense. All right. I understand it just a little bit better.
Awesome. So for instance, we could have an example where we want to find the probability of getting 3 successes out of 10 attempts when we know the probability of a success is 20%. So let's say we go back to that person shooting free throws, and now you've got somebody who's not as good at free throws, and they only make 20% of their free throws. And the question is, well, if during a given game, they, are fouled X number of times where they are given 10 free throw attempts, what's the probability that they will sink exactly 3 of them and miss 7 of them? Well, we can answer that with a binomial. And this is the formula for it. And it's a very complex looking formula, but it's actually a very simple formula to do. So let's throw in some numbers and see how it works. So n, as you can see, is the number of trials. We said that here, right? N equals 10. That's the number of trials or the number of attempts. Out of those attempts, we have 3 successes. So X is 3. And then the probability of a success is 20%. And that's what they call pi, pi for probability. Most formulas put a P here instead of a pi, but that's what this book does. So you can see that in the formula, right? N number of trials, that's 10. X number of successes, that's 3.
So
Probability
the
of a
pi-
success, that's
the pi
20%.
is not 3.1. It's not 3.14.
No, it's not the number pi. It's a variable. It's the Greek variable pi, which just represents the probability of a success. That's why I don't like them using pi. Usually the formula is written this way. The probability of X is n factorial. It's usually n's and x's, right? So x factorial and minus x factorial. And then instead of pi, it's p to the x and then q to the n minus x, where q equals 1 minus p. Q is the complement of p. This is a more common version of the formula, or they would just have 1 minus p here instead of q. So just pi is just a variable. It's not pi, it's just a stupid variable like x or anything else. So that's why it doesn't equal 3.1459, blah, blah, blah. It just equals, in this case, 20%, 0.2, because the success of them making a free throw was 20%. The only other thing that you have to realize in this formula is what the heck the exclamation point means, right? And it's not 10, it's not like an excited 10. This is a factorial. And factorial means that integer times every integer smaller than it down to 1. So 10 factorial is simply 10 times 9 times 8 times 7 times 6, 5, 4, 3, 2, and 1. And then you divide that by 3 factorial, right? So that's 3 times 2 times 1. And then 10 minus 3 is 7 factorial. So that's 7 times 6 times 5 times 4 times 3 times 2 times 1. And the nice thing is, look, these all cancel. And we really get 10 times 9 times 8 over 3 times 2 times 1. And then, of course, that's 720 over 6, which reduces to 120. This part right here is called a combination. It's the number of ways that you can rearrange things. It's called, in this case, it's an n choose x. It's if you have n many things, 10 of them, and you need to choose exactly 3 of them, how many ways can you do that? You can do it 120 ways. Because the idea is you basically have 10 free throws, 3, 4, 5, 6, 7, 8, 9, 10. If 3 of them are successes, well, that's 0.2, 0.2, 0.2. Those are the 3 that they made. But the 7 that they aren't going to make are the 80s, right? The 0.8, 0.8, 0.8, 0.8, 0.8, 0.8, and 0.8. Well, look at this. I've got 3 of the 2s, 7 of the 8s. Well, according to this formula, that's what I have right there. I've got 0.2 raised to the third power times 0.8 raised to the seventh power, right? Because the seventh power, according to this formula, is 10 minus 3. So that's where that all comes from. It comes from the idea that if they shot 10 free throws and they have to make exactly 3 of them, we know there's a 20% chance for each of the 3, and then there's an 80% chance they're going to miss the other 7. You multiply those all together. That's the probability of making 3 and missing 7. But there's nothing that says they have to make the first 3 and miss the last 7. They could be in any order, and that's where the 120 comes from. There's 120 ways that you can rearrange these things. But every time you rearrange it, it's still going to be this number, right? If we move them around and multiply them together, it's still going to be this number. So you would rearrange them, multiply together, get this number, rearrange them, multiply, get this number. Well, how many? And then you add those all together. Well, how many of those are going to be? 120. So that's why you take that and you multiply it by 120. That's where the formula comes from. Really, if you don't understand, who cares? Because do it in technology, right? Let SAS do it for you. Let your calculators do it for you. Let Excel do it for you. There's technology out the wazoo that will do binomials for you. So you don't really have to understand the formulas so much. It's nice to kind of have a basic understanding of what's going on, but it's not necessary in the least because you can always let SAS do it. And there's a very simple formula for SAS, and this is all in the SAS how-to guide. There are 2 types of these binomial probability formulas. There's a PDF for when you're doing a precise probability, and there's a CDF when you're doing a cumulative probability. So what the PDF does is this gives you the probability of exactly so many things. So for our previous example, we want to know the probability of exactly 3 out of 10, right? So we would have used a PDF. We would have done a PDF where X was 3 because we had exactly 3 successes. N was 10, that was our number of trials, and our probability of success was 0.2. And if we ran this, this would give us the probability of exactly 3 out of 10. And it's very simple. You just, you copy and paste the code into SAS, you run it, and it's going to spit out the answer a little bit more than 20%. Now, if they wanted to know the probability of other things that weren't precise things, like for instance, if they want to know the probability that he had less than or equal to 5 successes. So basically, he made 5 or fewer free throws. So that's, the number of successes was less than or equal to 5, i.e. so he made none, 1, 2, 3, 4, or 5, right? Any of those. Well, then you would do a CDF because that's a cumulative distribution function. And X is always the highest value. So a CDF function always adds up. So the CDF function always equals the probability of 0 plus the probability of 1 plus ... all the way up to the probability of whatever X is. So in this case, when you do 5, it's the probability of no free throws plus 1 plus 2 plus 3 plus 4 plus 5. Done. And that's what we want. We want 5 or less. But because this is a discrete probability distribution, if we said, what's the probability that he gets less than 6 free throws? Well, less than 6 means the exact same thing because you can't have 5.7 free throws, right? You can't have 5.9 or 5.5. If you're less than 6, you got to be 5 or fewer. So you can see how these 2 things give you the exact same code, because less than 6 still means you want the probability of 0 through 5. Questions on this one? Okay. The next 2 examples.
Is this code in your
yes.
cheat sheet?
Yes. Yes, it is. The next 2 examples, we have greater thans. So if we want to know the probability that X is greater than 4, and this is what I always tell my students, you really should do this every time so you can figure these things out, right? We've got a trial of 10. So we have the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. These basically represent how many successes we could have, right? Out of a sample of 10, he could eat, oh, sorry, we also have 0. He could make no free throws, 1 free throw, 2, 3, 4, all the way up to all 10 free throws, right? So if we want to know the probability that he makes more than 4 free throws, well, more than 4 is this. Circle what you want. I want that. Okay. We have to remember that our only option is either a CDF or a PDF. A PDF would give us one specific thing. So we would have to run PDF of 0, PDF of 1, PDF of 2, PDF of 3, and a PDF of 4, and add those 5 together if we want to do it with a PDF. That's a big fat pain in the ass. We don't want to do that. So instead, you go, hey, look at this. I know that CDFs always give me from 0 up to a certain point. That's how a CDF works. And in fact, if I run a CDF of 4, it's going to give me 0 through 4. And that's the exact opposite of what I want. So if I run this and then subtract it from 1, it's going to give me the leftover, right? Because if these all add up to, let's say, 30%, well, since probabilities have to add up to 1, I know if I subtract that from 1, it's going to give me the 70% that these are, right? So anytime you have greater thans or greater than or equal to's, you're going to be subtracting from 1 because your CDF is always a less than or equal to, right? It always gives you everything that's X or smaller. So again, being greater than or equal to 5, we would circle, oh, greater than or equal to 5 is all this junk. Oh, so it's the same thing. I just want 0 through 4. So let's look at a couple others. So again, we're back to the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's all possible answers. Okay, if I wanted you guys to find the probability that X was less than 7, well, that's 0 through 6 is less than 7. So that would be a CDF where X equals what?
6.
Very good.
X equals 6.
Thank you. Very good. If I wanted you to find the probability that X was greater than or equal to 3, let's say. Well, the probability that X is greater than or equal to 3 is 3 and above. So
I would do a CDF of 0 to 2. And
very
subtract
good. So X would equal 2. Perfect. Great job. And then what would we do with this number, this answer?
Subtract from 1.
Oh, you're a student. Perfect job. Awesome. All right. I don't need to keep beating that dead horse. You understand it. All right. The last thing we have to talk about is there is a way to compute the mean and the standard deviation of a binomial distribution. And it's very simple. The mean of a binomial distribution is simply n times p, which makes sense, right? If they make 20% of their free throws, then we would assume on average, every time they shoot 10 free throws, they should make 2 of them on average, right? So there's our n of 10 times our probability of success of 0.2 tells us that on average, they should make 2 out of 10. So that's where we get the average or the mean of a binomial distribution. And then the standard deviation is a little stranger. It's the square root of n times p times 1 minus p, or the q thing, right? So in this case, it's the square root of 10 times 0.2 times 0.8. And that's how we get 1.26. And that's just the standard deviation. That's just how you calculate it. The last type of probability distribution, discrete probability distributions that we're dealing with this week are the Poisson probability distribution. It's a French person's name. It's not, Poisson means fish in French. It also means poison. So it's neither of those things. A lot of people call it the Poisson distribution just because they don't know about the French, but I always feel like a pompous ass when I pronounce it Poisson, because that's how it's supposed to be pronounced. So we'll just call it the Poisson probability. But anyhow, it's a discrete one. It counts the number of successes, but the binomial distribution tells you how many successes you have given a certain number of trials, right? So if he shoots the basket 10 times, what's the probability that he gets exactly 3 free throws, right? That's a number of successes out of a number of trials. That's binomial. The Poisson probability says how many successes are you going to have over a given interval, usually an interval of time. So instead of out of 10 free throw attempts, it could be, you know, how many free throws is he going to make over an entire game? And then we would have to know on average how many free throws there are and that kind of stuff. And that's where this formula comes from, right? Where U equals 10 is kind of that, that average, right? So over that, in a game, there is an average of 10 free throws. That's where the U would be. That's where the 10 comes from. X is still our number of successes. So 4 successes down here. There's our 4 factorial. This U again is the same thing. It's that mean over the interval. And then this E, in this case, AO, this is the actual E. Like before, pi didn't mean pi, but here E does mean E, that 2.71 blah, blah, blah. So that is that actual thing.
Got it. Thank you.
Yeah. And again, who cares about the formula? Let's let the technology do the heavy lifting for you, right? So this code is also in the SAS how-to guide, and it can run it for you. So this would be the question: what's the probability that they make exactly free throws in a game, given that the average number of free throw attempts per game is 10, right? So it's that kind of thing where instead of we're just saying X out of 4 out of 10 attempts, we're just saying 4 over a given number of time, and then in that given number of time, we need to know an average. So it's kind of the same thing, but it's slightly different. Okay. Again, I cannot stress this enough. Please watch my videos on probability. It makes this a lot easier. Any questions?
I think I'm good, Dr. McBride. This is Madry.
Thanks, Madry. All right. So last, before we go, I just want to point out, here is our how-to guide, right? Right down here, week 4. Here are the probabilities that we use for week 4. And then here are the descriptive statistics, right, that we need for the week 4 homework. Here's the Poisson, the Poisson probabilities. And then here are the normal probabilities that really don't come into play until week 5. But they're all right there. All you got to do is copy and paste them. The easiest thing to do is when you're in SAS, just open anything, right? Just double click on anything, and it puts a little stuff over here on the window. Just hit edit, and now it gives you a clean one. Just highlight everything, delete it, go over here, copy it, Control C, come back over here, Control V, and there's my probability distribution. There's my binomial for exactly 0 out of 20. If I run that, there's my answer, right? And then I can go back to the code and go, okay, now I need exactly 3 out of 10 when it's a 25% chance of winning. Bam, boom, there it is, 25%. That's just pure coincidence that it was 25%. Okay, so it's that simple, guys. Let the technology do the heavy lifting for you. Christina.
Yeah, I have a question. So just on the guide on the binomial descriptive statistics by hand, I'm just looking through the homework problems because I've actually done them already. I don't think any of them asked for us to compute a standard deviation, unless I'm wrong. And I just missed it.
Let me see. I thought it was near the end. No, you're right. It's not until next week that you have to do that.
Okay, because I that's where I got confused, because I've read ahead, so that's where I thought that was coming in. I do have one question, just how to interpret one of the homework questions that I'm probably overthinking it.
Sure, go for it. Which one?
So hold on, I have it highlighted. Okay, so it's 423C, and so it's the probability that a randomly selected government employee with an advanced college degree has a spouse with a professional position.
Right.
So I mean, professional is mutually exclusive of an advanced degree, right? I mean, you get a professional position. I mean, is that the assumption? I'm just trying to, like, I'm probably overthinking this one.
No, I agree. The wording of this question is not great. Absolutely not great. And I have to remind myself of how they interpret it, to be quite honest, because I don't remember. Let's see.
I mean, what I thought on this one was it like the good over total, I thought would be, I had 460 plus, I'm trying to think of how I came up with this. I did this math, I'm like looking at my writing and I can't read my own writing.
Yeah, so this one, what they're saying, the probability that a randomly selected government employee having an advanced degree has a spouse with professional degree. What you have to realize is that, okay, according to this, right, government employees who have an advanced college degree produce the following responses to the offering of a promotion to a higher grade position that would involve moving to a new location. So what we're basically saying is that these government employees are already professionals.
Right.
So when they say the probability that a randomly selected government employee having an advanced college degree, so I guess we have to, right, because remember they all had advanced college degrees, so that kind of is that piece of information is like extraneous. Like we already know they have advanced college degrees. Stop telling me that. I already know that, right? So it's really just saying the probability that a randomly selected employee has a spouse with a professional position is literally just this column here. There was 460 of them that both spouses were professional, because obviously if both spouses are professional, that's because we're assuming the government employee is already a professional, and then their spouse being professional means that both of them are professionals. It's terribly worded the way this is. This one spouse professional basically means the employee is professional and their spouse is not.
That's where I was getting the 83%, so the 460 plus 370, because I was just thinking through this, like, could the government employee be a professional employed and have a spouse that's like, could they have a spouse that doesn't have an advanced degree but be professional?
Right,
like,
right. So
I was overthinking it.
Yeah, well, you weren't overthinking it. It's a poorly worded question. So what you have to, for these questions, you have to assume that the employees are already professionals.
Yep.
So when it says one spouse professional, it really should say spouse not professional, because this just means that the employee's spouse is not a professional.
Got it. Okay.
And then both spouse being a professional really just means that their spouse is a professional, because the employee already is a professional, right? So it's just terrible the way they labeled these things. So this question C, the probability that a randomly selected person has a spouse that's professional, is literally just 460 over 1,000.
Yeah.
46%.
Yeah. Okay.
But it's so poorly worded, people will always get that wrong.
Okay. That was why I was trying to understand if they were mutually exclusive or not, because I kept reading that and I was just like, okay.
No, it's terrible. It's terribly worded. I hate this question. It comes up every time and it's just so poorly worded.
Okay. Thank you.
Yep, of course. Any others?
Yes, I have a question from the link I posted, which is my article. And the bottom of that page 5, it talks about a cost, the k-means. If you go to page 5, and then the last paragraph talks about the k-means being one of the most popular unsupervised clustering algorithms. And then I was looking for the dependent variables in the article, and right there it talks about the cost function, which is in that same paragraph, is dependent on 3 variables, which is the index of the cluster and so on. I'm not sure if that would be okay, because the question says dependent variables.
Yeah, absolutely. Yeah, the cost function is dependent on 3 variables. I mean, I don't think it's technically not what are you talking about? So in the instructions for
the discussion,
the discussion, does it say identify the dependent variables?
Yeah.
I think that's only if you have a correlation, right?
It says variables including which are dependent and independent.
Oh, okay. If any. Yeah, as well as the conceptual. So usually we only talk about dependent and independent variables when we have correlation or regression, right? Something is related to something else.
So not as important here.
Yeah, this is not what this means. This is just saying that the cost function is basically built on these three things, that they're what drives the bus. Depending on the values that you get for those three variables, that's going to tell you what the cost is. And that's not really an independent dependent kind of thing, because there's really not a correlation. Although technically there is a correlation, because you've built it. The cost literally equals this times this times this. Well, then the cost is absolutely going to be correlated to those things, because it's equated to it.
Understood.
You see what I'm saying? So it kind of works, but it's not really a true correlation kind of thing. So that's why it says if any. Yours isn't really dealing with correlation, so you really don't have any of that. Okay.
And then it talks about k-means. I don't think we're covering that in this class, right?
Hell, we don't cover that anywhere. This is extremely advanced stuff.
Because this is in line with my actual research topic.
That's awesome.
This paper. But the fact that it's so advanced is not covered even in advanced stats it's worrisome.
Yeah, well, I mean, in truth, k-means is really just this idea that you're adding up k many things. It seems like to me. I'd have to read more on this, but from what I'm looking at, it looks like that's what k-means is. One of the clustering algorithms for automatic data grouping in component clusters tries to group the so it groups the data into k clusters, right? So k-means basically just says you've got a bunch of data and you're going to put them in clusters, right? You're going to put them in like subsets. And then you're going to calculate the means of all those subsets. And we're going to call those means k-means because we had k many clusters.
Okay, got it.
Yeah. So that's what it is. I mean, it's not really that advanced. It's just this symbology, would make most people's heads explode. But once you start breaking it down, it's pretty basic stuff.
Okay. Thank you.
Yep. Anything else?
So Dr. McBride, I have a question of 421A. And then the B is also compute the probability of occurrence of event T1 when W, so like the donors who are white and have a
Yeah.
blood type O. So what's the difference between the event T1 over / W and P T1?
So the event is just what we call it. So for instance, the event of T1 / W means the event that the donor has type O blood, given that they're white. So that's what this would be in words.
Right. And then the second.
And then this is just saying, what's the probability of that happening? Well, what's the probability that they have type O blood, given that they're white? Well, given that they're white means we're only looking at these four things, right? This is our new subtotal. And out of all of those numbers, having O blood is a 36% chance. So it'd be 36 over 36 plus 32.2 plus 8.8 plus 3.2, whatever that whole sum is. So it ends up being whatever that is.
So the term after comma is, they are describing this whole sentence. So PT1 over
Yes.
W.
Yes.
Okay, got it.
This means calculate the probability of T1 given W.
Okay, got it.
That's what that symbology means.
So how would they calculate the event of T1 and W? What would be the symbology for that? So we could differentiate it.
So the probability of T1 and W would be the probability of T1 and W.
Oh.
This is and then this is or.
And
So
then
the
the
pro,
slash
so,
is given.
so like up here, the probability of Asian and O would be the probability of Asian and O, that kind of thing.
Okay.
Yeah, I don't know if they use those symbols anywhere in the homework. I don't, oh, here we go. Yeah. So this is an and, this is an or.
Got it.
Anything else?
And our final answers are in percentage, and we are doing the whole number. Like, let's say if it's 0.4488, is it going to be 45% probability, or is it 44.88%?
I would rather that you just leave your answers as decimals, rounded to 4 decimal places. If you want to do percentages, then round them to 2 decimal places, right? So basically, your answer is either going to be 0.4583 or 45.83%.
Okay, got it.
Anything else? All right, great questions, everybody. Thanks for showing up. And I will hopefully see you guys Wednesday. No, sorry, Thursday. Right, let me double check. Thursday with more homework questions. And don't forget, Thursday is also when your critique is done or due. All
And
right,
what time is the pre-turn-in time on Friday?
back to the normal 9 a.m. Eastern time, 6 a.m.
Okay.
my time. The truth of
All
the matter is, as long as it's in my, it's turned in by the time I sit down and start grading it, I'll do it. But I can't guarantee you that I won't grade, any later than 6 a.m. I get up early, but if I don't grade until 9 a.m. and you turn it in, later, you could luck out. But I can only guarantee that you won't be late as long as it's in by 9 a.m. Eastern, 6 a.m. my time. But chances are I might sleep in.
Yeah, you saw how I got mine in this week because we had days off. So
Yeah. So just get it in Friday by 9 a.m. Eastern time. You'll be fine.
all right, good deal.
All right. See you guys Thursday.
Good night,
Thank you.
everybody.
See you.
Good night, everybody.
Thanks.